Hi, my name is Dr. Ed Borain from the Johns Hopkins University Applied Physics Laboratory.
And I'm Sarah Heiner. Together, we are presenting a novel approach to transport layer security for spacecraft constellations.
We all understand the benefit that satellite constellations can provide. And when we talk about networked constellations, we start asking questions about what do these data flows look like? Are we simply talking about cases where something would bent pipe data, or are we talking about constellations that will be communicating amongst themselves in ways that start looking like a traditional terrestrial network, such that now this node is a spacecraft and this node is a spacecraft? Can you build a network that includes spacecraft and secure it in the same way? We treat networking as a series of roles and responsibilities typically decomposed into layers. We'll see an application layer, typically a transport layer, a networking layer, a MAC-PHY layer. It is a logical decomposition of roles and responsibilities. We physically implement these logical roles and responsibilities through encapsulation. We would take some application data, encapsulate it in a transport packet, which would then be encapsulated in a networking packet, which would then be encapsulated in a MAC frame. And then the relationship between all of these data are such that certain amounts of data are hidden based on the levels. In order to answer the question, is there a better way, we need to take a little bit of time and look at how things are done today. Typically, we use IPsec. In a transport mode, the data or the payload associated with that packet would be the thing that would be encrypted. In tunnel mode, you would also want to hide the header of your additional packet. And really, the only way to do that is to take that entire packet and make it the data segment of a brand new packet. Apply additional header integrity and confidentiality on top of this new payload made out of the old original packet. If we then talk about the transport layer, TLS protocols start by doing some level of key negotiation, and then the payloads within TLS are segmented into a series of records. The difficulty with TLS, of course, is that it requires a reliable transport mechanism. If you do not have TCP, then there is a datagram transport layer security protocol, DTLS, and it is a recognition both that it is a good idea to carry cryptographic material in packet headers, much like we see in IPsec, but also a recognition that you cannot always rely on endpoints to stay synchronized and have in-order delivery, even on the terrestrial internet. In looking at the ways in which IPsec and TLS and DTLS have been designed, something became apparent. The ability of the underlying transport protocols to hold information and carry it was utilized by the security protocols associated with them. If we then try and apply the same approach to space, a question becomes, are there other protocols being considered for spaceflight that give us new and motivating features? And one of those is the bundle protocol. The bundle protocol was originally designed for communications in deep space, where you could not synchronize information between endpoints in the network. And if you cannot synchronize information at endpoints in the network, the other alternative is to carry all of that information with you. And to enable that kind of use case, the bundle protocol has a syntax for very featureful secondary headers. How could you use these additional secondary headers and the idea of carrying session information with the bundle to build new security features? A bundle protocol data unit is considered a bundle of blocks. You have a primary block and a payload block, but then you can have 0 or more extension blocks. If you have a particular bundle node that receives a bundle, and that bundle has a primary block, 1 or 2 extension blocks, and a payload block, that node can process one of the extension blocks, update that extension block, and that extension block can carry information to a downstream node. If you then combine the idea of placing cryptographic material inside of extension blocks associated with how we have signed or encrypted the payload block, and you combine that with a policy located on the nodes as to what blocks should or should not be in a bundle and what security services should or should not be active in the network, then you can put together a different approach, augmenting in a more flat space this kind of information in a bundle itself. Communication networks, these constellation networks, are going to have a series of stresses. Clearly, if you have LEO spacecraft, there are both planned and unplanned service disruptions. If we get to a point where we have very high rate inter-satellite links, we would still see traffic that could swamp that. A single 4K video stream would saturate a 10 gigabit per second link. How would we deal with congested paths such that we might want to change the endpoints of our security tunnels instead of collapsing the security tunnels and trying to reestablish them at a later time? These come together to say that we may have partitions in that network. At that point, spacecraft either can choose to throw away their data, or they can start storing their data and hope that there is a time in the future when the connection would be reestablished, then data would be able to flow again. The ability to measure individual link state. Even if you are directly involved in one link, you are not going to be able to really push all of that immediate link state information. We're going to have to deal with multiple administrative domains. Portions of a network which might be administered by organization A, and then there would be different users of that network, which would perhaps be administered by organization B. And then there may also be the ability to federate infrastructure to take overflow data, either indirectly or directly, which could be then administered by yet another organization. What a new security protocol would have to do are these 5 things. The first is a fine-grained packet security. The ability to target individual contents of a packet gives a flatter security namespace. And what that leads to is a concept of augmentation before encapsulation. If you can augment headers in a flatter space as opposed to hierarchically applying encapsulation, the delay tolerance allows information to be stored along with the packets in a fine-grained way while a packet is put off into persistent storage. That leads to a topological independence. You are able to have a flatter security space. Then you have achieved more self-sufficiency in the security stance of the packet itself. The most important concept and the focus of our paper is this ability to do more through augmentation than through encapsulation. And we illustrate that approach here. Security using augmentation doesn't need to take this and rewrap it. What it can do instead is use a flatter header space to apply individual security results without this kind of layering.
We are presenting Bundle Protocol Security, or BPSec. BPSec incorporates best practices from several protocols, which is illustrated by the table that you see on the right. BPSec extension headers can hold security information and can also be the targets of a security service. Security services are applied based on need, which allows different cipher suites to be applied to different blocks within the bundle. The support of these features is enabled by BPSec's use of the bundle protocol, as well as the 5 design properties that are called out here. These design principles allow BPSec to be more than just the union of these best practices. Block-level granularity, our first design principle, allows different security operations to target different types of information in the bundle. Second, multiple nodes have the ability to add security blocks to the bundle. Mixed security policy allows each BPSec node to determine its role by policy at that node. And user-selectable security contexts enable BPSec to operate in environments where there isn't any negotiated information between a security source and endpoint. A security context can contain all of the information needed to process a security operation in the bundle. Finally, deterministic processing assures that the processing order of security services in a bundle is certain. BPSec currently supports 2 security blocks and allows for new security blocks to be standardized over time. The block confidentiality block, or BCB, is used to add a confidentiality service to the bundle. When a BCB is added, the contents of its target blocks are encrypted in place, using an AEAD cipher in order to generate signed ciphertext. When the BCB is removed from the bundle, its targets are decrypted and any additional authentication information that was generated is verified. The block integrity block, or BIB, is used to provide plaintext integrity for its target blocks. The outputs of the integrity mechanism are stored as security results belonging to the BIB and can be used to verify the target block's integrity during transit and at its security endpoint. The processing role of any BP node is determined by policy. As you can see in the diagram here, the policy input is provided to the bundle processing portion of this bundle processing agent, which allows it to identify itself as a security source, meaning that it's responsible for adding a security block to the bundle. The bundle is passed to the security services portion of the BPA, which uses policy to identify the target block and what security service has to be added to the bundle. During transmission, a bundle may encounter security verifiers. The security verifier is responsible for ensuring that the target data of the security block has not been modified. In this figure, the bundle is received by a node which policy identifies as a security verifier. The security block is processed by the security services portion of the BPA to verify the contents of its target block. It is important to note that the bundle is not modified by the security verifier. A node that is identified by policy as a security acceptor is the endpoint of a security operation in the bundle. The security acceptor is responsible for both processing and removing a security block from the bundle. When the bundle is first received by the security acceptor, it contains both a security block and target block. The security block is first processed. When a BCB is processed, the target block is decrypted. When a BIB is processed, the integrity of the target block is verified. Once the security block has been processed, it is removed from the bundle. This figure shows an example security workflow. 3 bundles are transmitted by both security-aware nodes, bundle nodes 1, 3, and 4, and non-security-aware nodes, which is bundle node 2. The role of a security-aware node is determined on a bundle-by-bundle basis, not by the node itself. This allows a node to take on multiple roles, which can be seen by bundle node 3. It is the security source for bundle 3, the security verifier for bundle 2, and the security acceptor for bundle 1. BPSec takes an augmentation before encapsulation approach, which provides 2 key benefits. First, augmentation does not constrain the architecture as encapsulation does. Second, augmentation allows tunnels to overlap, supporting overlapping policy in the network. This figure shows the transmission of a bundle between nodes 1 and 6. End-to-end primary block integrity is provided simply by node 1 adding a BIB to the bundle, and node 6 acting as its security acceptor. Node 2 may represent a policy gateway requiring a payload confidentiality tunnel. Where other protocols would take an encapsulation approach, BPSec treats policy gateways as security sources, so node 2 adds a BCB targeting the payload to provide confidentiality. Overlapping policy is then encountered at node 3, where confidentiality is required for an additional extension block. This could not be supported by an encapsulation approach alone. However, augmentation can be used to support overlapping tunnels. The necessary extension block and BCB are added by node 3, which acts as an additional security source. The 2 BCBs present in the bundle transmitted between nodes 3 and 4 represent the overlapping confidentiality tunnels.
In conclusion, what we have presented today is a network security approach based on augmentation by using different and emerging features in new transport protocols such as the bundle protocol. Certainly, the protocols that we use for security on the terrestrial internet create secure networks, but they do so by constraining the trade space in how we architect our systems, which could lead to more expensive or less efficient or less flexible networks. We hope that this presentation has made you think more about how networks are secured and how they might be secured in space networks. Thank you very much for your time today.